Hi there, my name is Tirso Varela Rodeiro, and today we are here to talk about our new work, Semantrix, or a compressed semantic matrix. First of all, thanks for watching this video as part of your quarantine. I will try to explain the easiest way possible, but if you have any doubts or you want to have deeper knowledge about this structure, please read the full paper or feel free to contact me. Let's do this. As you may know, I will talk a lot about trajectories, so here is our route map for today, a classic one. Our first stop is Introduction. Let's talk about my problem. What is this all really about? Whoa, alright, let's start from the very beginning. Right now, we should be here. But I am here, and apparently I will be here for a long time. Well, more precisely, I am here. And even more precisely, here, Coruña. What do you care about where I am right now? Well, you already may know a couple of things from my land. Probably you have heard of Santiago de Compostela Cathedral, with his Camino de Santiago, or Way of St. James, having pilgrims from all around the world. Or maybe you are more into sports. We have a soccer team called Deportivo de La Coruña. We used to be really good. We even appeared in Captain Tsubasa. And if you do not recognize anything of this, I am sure you have seen one of these shops. There is even one in Salt Lake City. But in Spain, we are famous for our foods. Besides seafood, we export large quantities of the products you can see on screen: cheese, milk, meat, etc. And what do they all have in common? Exactly, they all come from cows. And of course, when orders rise, producers grow, and grow, and grow. And everything was fine, the economy was fine, jobs were created, people were happy, but then early 2000s arrived. What a funny time to talk about this. So the bobbing spongiform encephalopathy appeared, also known as mad cow disease. Everything changed overnight. It was dangerous to let people at farms manage their own waste, so from that time until now, there are only a few companies that can do the work. And a lot of logistic problems appeared. Luckily, these protocols have been improved over the years, and some time ago they started to demand some tasks to our research group. As I do not have time to explain in this video all the work we have done together, I will just talk about the new part, driver trajectories and their meaning. We have already reached our second stop. Among all the track trajectories problems, what are we tackling here? As someone said, to understand the future, we have to go back in time. My supervisor published one paper back in 2017 where they were able to break a trajectory into several segments and identify what activity was doing the track driver during each segment. And they accomplished that just using the phones of the drivers. But what can a driver do? We can agree that most of the time he or she will be stuck into one of these. Maybe he's at headquarters beginning his route, or maybe she is at the farm of a client, or maybe she is just driving on a planned route or taking a break at the gas station. Once we know what our drivers are doing, what should we do? That is why we are here for. We need a compressed representation for this information that let us query it efficiently. Let's start with an easy example, a naive approach. We have a two-dimensional matrix. The columns of this matrix represent time intervals, and the rows are each of my vehicles. We store for each track in each time interval the code of the activity what he or she was doing. For example, the car was performing the activity with ID 4 from 120 to 130, as we can see inside the black circle. What can we solve with this? We tackle three kinds of queries: individual queries, pattern queries, and aggregated queries, focusing especially on the latter ones. An individual query could be what was doing driver 4 at 1:30, as we have just seen before, or which are the activities performed by driver 3 between 1 and 1:30. In our naive representation, we can easily solve this question like this: activities 1, 3, and 5. When we ask for patterns, we ask something like how many times activity 1 was followed by activity 3. And now things get a bit more complicated in our naive approach, as we need to visit all the cells in the matrix, saving those that satisfy our query. And last but not least, aggregation. We need to solve questions like how much time was actually spent at headquarters by all the mobile objects. First, we have to know that being at headquarters is activity 1, so we need to count how many ones we have in the matrix. Again, we need to travel around the matrix gathering activities to solve this query. Everything clear about the problem? Excellent. So, start the stop. Our proposal. Now we all know the secrets of this simple matrix, so we can go deeper. First, let's transform our matrix into an array. We do that splitting the rows as we see in the figure. And we append one before another until we have something like this. As you can see by the different shades and the vehicles, we have exactly the same information. We have had a matrix and now we just changed it into an array. And now it's where it starts. Based on our array, we create a header array, which is just the same information without repetition. As you can see, above we have 11377, and the header array says 137. Then we have 13317, and the header array says 1317, and so on and so on. In between, now we have a bitmap. We use this bitmap just to know if a number is repeated. So we have a 0 for each repeated number. Again, we have 11377, that is 10110, and so on. And that's it. We don't need the first array anymore. But we still have the same information. Easy, right? Alright. For my next trick, I need to have a flashback. In 1984, a paper called Summed Area Tables for Texture Mapping was published, and it explained a really clever way of having the sum of any submatrix within a matrix. How do he manage to achieve that? Please, look at the first matrix. We have just random numbers, okay? The second matrix, matrix B, stores the aggregation of those first numbers. That is, it sums everything from the top left to the right bottom cell. Beginning in the first row, 2 plus 4 is 6, plus 3 is 9. It's 0. The second row is 2 plus 1, that is 3, plus 4 plus 3, that is 10, and so on. So now, if we want to calculate the sum of every cell in the gray shade, we have two options. Or we sum each cell of the first submatrix, or we operate like in the last matrix. That is, to the total area until the last cell we need to sum, in this case 64, we subtract the sum of the upper area, in this particular case 19, and the area on the left, 18, as you can see. And as we have subtracted the upper left area twice, 6, we need to add it once. So we can calculate in constant time 64 minus 19 minus 18 plus 6 equals 33. If you did not get all the details, don't worry, we will do another example together. Continuing with the previous example, now we're going to build our own aggregated matrices. We need one aggregated matrix per activity. As you can see in the figure, the first column of the aggregated matrix for activity 1 collects the ones in the first column of the naive matrix. So 1 is 1, plus 1 is 2, plus 1 is 3, and so on. In the second column, we keep summing ones, so the first row is 1 plus 1, that is 2. The second row has the sum of the ones appearing in the 4 cells in the upper left border, 1 plus 1 plus 1 plus 0. and so on. Here we can see the full aggregated matrix for activity 1. And we will have one for each different activity. As an example, we can see in screen matrices for activity 3 and activity 7. Once again, look that we have a lot of zeros in activity 7, because there are no 7s in the upper left quadrant of the naive matrix. And that's it. Now we know what Semantrix is. Let's see how it works. We will now answer the same queries as before. First, an individual query. Which is the list of activities performed by a given driver between 1 and 130? As we know, in the naive matrix, we just need to retrieve these cells. In our structure, we query the same period of time, so we need these 3 cells too. But also, we need to know which activities are. So, as we only have 2 ones in the bitmap, we just need the first 2 cells of the header sequence. That is 1 and 8. Now let's do a pattern query. How many times activity 1 was followed by activity 3? If we recall the first part of representation, we got something like this. In our case, we just need to do the same search in our headers array. As now we have an array, we can use an FM index to boost our search. And now our main focus, aggregated queries. How much time was actually spent at headquarters ID 1 by the 3 last vehicles? In the naive matrix, we need to count how many times activity 1 appears in the last 3 rows. In Semantrix, we are just using the expression we have seen in the flashback. In order to simplify the idea, imagine that our aggregated matrices are surrounded by zeros. What we want in practice is to calculate the sum of this yellow submatrix. Applying the expression, we just need to access 4 cells, the borders. And this is how in constant time we can achieve the same result, 9 minus 0 minus 4 plus 0 equals 5. Hopefully everything is clear at this point. So let's have a look to our results. For comparison purposes, we have created a simple version of Semantrix that we will call baseline plus. We have a sequence of activities as we understand by now, and instead of having an aggregated matrix for each activity, we only have one big matrix with aggregated rows. In this way, we see that in the 9th row, the last one, we only have zeros until the first 9 appears in the sequence. Measuring space, we get no surprises. Of course, the naive matrix is much smaller than the other solutions. It is worth to mention that we improve our compression using samplings in our aggregated matrices, represented in this figure by diff. Talking about time, we can see that again, individual queries are easily performed by the naive solution as it has direct access to the cells of the solution. However, here is where the naive solution is in trouble. In both aggregated and pattern queries, the naive solution needs to travel each cell of the matrix. Instead, using the FM index over our header array and the summed area tables formula, we can solve the queries much faster. So we have solved our main problem and we are one step closer to achieve the trajectory data warehouse. Final stop, future work. So now we have a structure to handle trajectories and activities. We can do 3 kinds of queries and solve aggregations really fast. What do we need now? We need geometries. In this work, we know what, when, and who, but it will be interesting to know where, right? So adding the geometry to each trajectory will make an interesting tool, but also a complex problem. The idea opens a wide new field of possibilities to perform queries combining spatial, temporal, and semantic constraints. And with this, we have reached the end of the route. Again, I have tried to simplify everything in this video, so if you want to go deeper, please read the full version of the paper. Also, here is my email, and feel free to ask me anything. Thank you for your time and your attention, and see you next year.